Well, our next speaker is Professor Jingjing Ma, and his title is Infinite Primes for Rings.
Okay, I'll go over field definition first. In a subset is of ring called a preprime if it is closed under addition, multiplication, and not including -1. A maximal preprime is called a prime by Zorn's lemma. Every prime is containing a prime. A prime S is called infinite if one is in S, otherwise S is called finite. Infinite prime S of R is called 4 if R is equal to S minus S. So the S minus S will be the subring generated by S. So this definition was given by Harrison around 1966. Here definition for partial order. So I think I'm familiar, but I won't leave here so we can compare. And now here subset P of ring is called the positive cone. Just call this a partial order. P is closed under addition, multiplication, and also positive part intersection, negative part will be 0. A partial order is called directed if R is R P minus P. So any element is a difference of two positive elements. By Zorn's lemma, each partial order is containing a maximum partial order. If P is a maximum partial order, it's pretty easy to verify one must be in P. So those two definitions are pretty close. The difference is here, -1 not in S. Partial order of having a section would be 0. So I was wondering what's the connection between those two concepts. For example, if we have maximum partial order, then because 1 is in P, then -1 is not in P. So P will be a preprime, okay, for sure. So the P will contain a infinite primes. To my knowledge, nobody in partial order ring has used infinite prime to do some proof, to get some proofs in the partial order ring. So this talk, I'm going to show you we could use this infinite prime to answer some questions in partial order ring. I first learned infinite prime about 3 years ago. That time I was working on.
I usually just hit the space bar.
Okay. Yeah.
As long as we have the mouse in the window.
Okay. So the field R field is called O star. If its partial order on F can be extended to a total order. So it's included in a total order. The number field is a subfield of complex numbers and the finite-dimensional over rational numbers. So we want to determine which number fields are O star. That's the open question in Steinberg's book. Harrison proved some very nice results about infinite primes of number field. So let R be a number field is n-dimensional over Q, then they exist exactly an isomorphism. I'll call them as embeddings because they are really isomorphism is 1-to-1 from R to complex field. Those embeddings, this will be the standard complex conjugate. So for sigma 1 to sigma R, this will be the real embeddings. So it will be the embedding from R to real numbers. The rest will be the complex embeddings. So it will be embedding from this number field to complex field. Certainly R may be 0, and this complex embedding maybe 0. Okay, that's possible. And he proved the following result: when R be a number field and sigma 1, sigma R be infinite prime divisors. So I call those as a real embeddings. And the set of inverse image of those embeddings of non-negative real numbers are all distinct and consist exactly of all the infinite primes of R. So this would be a characterization for the full infinite prime of this number field. For a infinite prime which is not full, then there exists a complex embedding such that P is equal to inverse image of this complex embedding of non-real numbers. So from here, especially if you look at 3.5, so each of those inverse image of R plus will be a total order, right? Certainly will be a total order. So looks like 4 infinite primes of R will be total orders. So now we realize we can prove the following. For a number field, infinite primes are exactly maximal partial orders will be the same. So proof is pretty straightforward. We know the maximal partial orders will be containing a infinite prime. Then we just need to show this infinite prime is a partial order. That's all we need to do. Okay, then it must be equal. Then by using this result, we can give some conditions for a number field to be O star. So one condition will be a number field is O star if and only if each maximal partial order is derivative. So if we have number field is O star, then maximum partial order will be containing a total order, then it must be equal. But total order will be derivative. So this direction is true. For another direction, if you have partial order that is containing a maximum partial order, is it derivative? Then if we use Harrison's result 3.5, then we know this full infinite prime must be a total order pair. So now by using this result, we can produce a lot O-star field. For example, because this talk is not about O-star field. Let me just give you some example. One example would be you have a O-star real number field. The dimension over Q is a prime number. Then this F must be O-star.
Jingjing,
Go
when you
ahead.
say real number field, you mean it's actually separating the reals? What do you mean by real number field?
Right, yes.
So-
It's suffering of reals. That's right. Yes. Yes. Generally, it will be suffering of C.
Right.
Right, yes. That's some real numbers there.
Okay.
At least. I do want to give you a counterexample to show a maximum partial order which is not derivative. For example, we take alpha as the fourth root of 2. Then we do the field extension by adding alpha to Q. Then we define this P. This will be a partial order. So addition is closed and closed very clear. For multiplication is closed because this negative alpha square will be 2. Okay, so multiplication will be closed. Then this will be a partial order. It is not derivative because alpha is not in the P minus P, right? Because this we only have alpha square here. Okay. Then this will be a maximal because P is not containing any total order. Because any total order alpha square must be positive. We cannot have negative alpha square in P. Also, another way to look at this P, we can use an embedding from F to complex field. We will send this alpha to I times alpha. I is an imaginary unit, so I square is equal to -1. Then we have the P is equal to inverse image of this embedding. So this will be a massive partial order, but it's not derivative. So this field is not O star. It's not O star. So this for number field. So we know the maximum partial order and infinite primes are identical, but how about general situation. Actually, we have for any field, each maximum partial order will be an infinite prime. However, infinite primes may not be maximum partial orders. Here's an example. So we take a polynomial ring over Q. We define a polynomial is positive if the lowest term of the term of coefficient of the term of lowest power is a positive rational number. Then we know this is the total order, right? The total order on this polynomial ring. Then we define this S is all polynomials such that the constant coefficient will be a positive rational number over 0. So this will be a infinite prime. And the intersection will be all polynomial with a 0 constant. We support F is the quotient field of this polynomial ring. So this S will be a preprime in F. So we can extend S to S1. S1 will be an infinite prime. S1 cannot be a partial order. Maximum partial order cannot be a partial order because intersection S1 and the negative S1 contains intersection S and negative S. So it's not 0. Okay, it's not 0. So it's not a partial order. So this shows number 2 is not true. Is true. So infinite prime may not be a maximum partial order. Also, this example shows number 1 is not true for a integral domain because Q of X is integral domain. We have a partial order, total order actually. It's probably properly containing a infinite prime. So for integral domain, a maximum partial order may not be an infinite prime. However, we still can use this result to prove some result in partial order ring. One result, I believe it was true for a long time, but I didn't know how to prove. A Archimedean for a field, a Archimedean directed maximum partial order must be the total order. I didn't know how to do the proof, but we can use infinite prime to give a proof. So first, let's recall the definition for Archimedean. So a partial order ring is called Archimedean. You will find elements if n times a less than or equal to b for all integers. A will be 0. Also called strong Archimedean. If one is positive and any positive element be less than or equal to a positive integer. This strong Archimedean is called Archimedean by Harrison and Dubois. But I believe the earliest definition for Archimedean I know from the Berghoff's book, Logic Theory. So that's around 1940 something. That's the earliest I know. So I want to keep this terminology here. So I use a strong Archimedean for Archimedean by Harrison and Dubois. For a total order, Archimedean and strong Archimedean will be equivalent, will be the same. But if we have class order field, which is strong Archimedean, then the order must be total order. But certainly Archimedean mass order field may not be a total order field. So I feel Archimedean by Harrison and Dubois is stronger. Okay, so that's why I use this name. Harrison gave the following result about infinite prime, which is strong Archimedean. So let P be a strong Archimedean infinite prime. Then there's a unique ring homomorphism from the ring generated by P to the field of real numbers, such that the P will be the inverse image of this homomorphism of non-negative real numbers. And the P intersection, negative P will be the kernel of this homomorphism. Because in this result, we don't assume this R is commutative, but now we know this will be P minus P over P intersection. That P will be isomorphic to a subring of real, so this will be commutative. So by using this result, then we can prove the following. So let F be a field and P be a maximum partial order on F, that is our PPD. Then if P is directed, then there is a embedding from F to R such that P is the inverse image of negative real numbers. So, but this is a total order. So in particular, P will be a total order. If not directed, then that embedding from F to C, and the P will be the inverse image of negative real numbers. Also, this result was generalized to universal domains. So let D be a universal domain, and P be a Archimedean directed maximum partial order, and P must be a total order. So we know right now for number field, maximum partial orders and the infinite primes are the same. So how about the next one? Certainly we will consider algebraic case. But for that situation, we are going to consider it more generally, and not only for field, consider a universal domain. Then we have the following result. So let D be a universal domain that is algebraic over Z. And maximum partial orders on D and the infinite primes of D will be the same. Now also improve each maximum partial order is strong Archimedean. So proof is similar to a number field situation. So we have maximum partial order. This will be the preprime, so it containing a infinite prime. Then we just need to show this infinite prime will be a partial order, so they must be the same. They must be equal. That's the same idea. Certainly, it's a little bit more complicated, but it's not too bad. By using this result, we can prove the following result. This is a very important theorem. So let D be an universal domain that is algebraic over Z. Each directed maximum partial order on D must be the total order, Archimedean total order. Let F be a field, and so this is so D is algebraic over Z will be a sufficient condition for each maximum partial order to be a total order, but I don't know if this condition is necessary or not. So far, to prove that also I cannot find a common example. However, for a field, it is a necessary condition. So let F be a field, then F is algebraic over Q, if and only if each directed maximum partial order on F is an Archimedean total order. So for necessary part, was proved by Dubois, Schwartz, and Yang, prove if a field F is not algebraic over Q, then F has directed partial orders that are not total order. I go back to this topic later. So from here, we can answer some other questions. After Schwartz and Yang prove this, then they ask question, following question. So a field is called non-real if it does not carry a total order. So they state if remains an open question whether non-real algebraic number field carry a directed partial order, because they prove if not algebraic, then the field will carry a directed partial order. Now by theorem 6, the answer is no, because if that's directed partial order, then this directed partial order will be containing a directed maximum partial order, but we know by theorem 6, directed maximum partial order will be the total order. That's so that's not possible because we assume the field is non-real. Also, let Q bar be the field of algebraic numbers over Q, Z bar be the integer algebraic integers over Z. Then Schwarz proved that Q bar cannot be a partial order field. Now by using theorem 6, Q bar cannot be a partial order field with a directed partial order. And the Z bar cannot be a partial order field or ring with a directed partial order because, for example, for Q bar, if that's a directed partial order, then again it is containing a directed maximum partial order. The Q bar is algebraic over Q, so that directed maximum partial order must be a total order, but the Q bar cannot have a total order because I is there, so I square is equal to 91. It's in Q bar. Same thing for Z bar, so they cannot be true. So the result was generalized from the lattice situation to the directed partial order situation. Okay, now let F be a subfield of R. And we consider the complex field C is equal to F of I in the complex field. Now, Burkhoff and Pierce asked if the complex field over root can be made into a partial order field. More generally, we may ask if C, the complex field over any subfield of R can be a partial order field. So by using again theorem 6, if F is algebraic over Q, then C complex field over F cannot be a partial order field with a directed partial order. So in particular, C cannot be a partial order field because partial order is directed. Now this result also generalized to the evasion algebra of quaternions. So if F is algebraic, then the quaternions over F cannot have directed partial order to make it into a partial order algebra over F. Okay, a partial order ring with negative square is a partial order ring with an element A such that A squared will be less than 0. Yan first noticed there are many directed partial order rings with negative square. For example, for C, I mentioned before because it's not algebraic over Q, so it has directed partial orders. But that directed partial order also with one is positive. Because when it's positive, then we know the I square will be negative, will be less than 0. We have many rings. Now we can prove the following. So let D be an integral domain that is algebraic over Z, then D does not have directed partial order with negative square. So this result is generalized to an arbitrary commutative ring. So let R be a commutative ring that is algebraic over Z. Then R does not have directed partial order such that A squared less than 0 for some regular element. For the regular means it's not 0 divided. Certainly for integral domain, every non-zero element will be regular. So this will be generalization part 2 to part 1. Then we have this more general result. So for any commutative ring that is algebraic over Z, if R contains an element I squared is equal to 91, then R cannot have direct partial orders. In particular, R cannot be a large order ring, so that's not possible. Because large order is a directed order. Okay. So the Burkhoff and Pierce asked the question if C can be a large order ring. This question is still open, we don't know the answer yet. So it's an open question. This is in Burhoff-Pierce 1956 paper. It had a long history, but still do not answer. So in an effort to answer Burhoff and Pierce question, Schwartz and Yan in 2011 mentioned before produced derivative partial orders on C. Any field, when density degree will be bigger than equal to 1, then we'll have derivative partial order to make them part of the field. Especially C has derivative partial orders. So now we know C has derivative partial orders, but still we don't know if C has Lattice orders or not. This result was proved by Dubois in 1970, actually, using the language of infinite prime of field. So I want to briefly present his proof because I think his proof is more direct and also maybe applied to other areas like integral domain. So here are a few definitions. I'm too fast because. So let F be a field, P be a maximal partial order. So I'm going to use maximal partial order. Dubois was using infinite prime. So we define those two sets. So B sub P would be the element in F. That the positive integer n minus a P a n plus a was P. And J sub P will be all elements in F. So 1 plus M8 will be P for all integer M. Then this will be the subring terminated by P. So P. It is pretty routine to check A sub P is a subring of F and J sub P is an ideal of A sub P. Also, those are some basic properties for a massive partial order on a field. So any subring containing P will be a subfield. So in particular, E sub P will be a subfield. P is infinite prime. I mentioned this before. And F will be algebraic over P over this subfield. And E sub P is a quotient field of B sub P in this field. So those properties can be verified pretty straightforward. Now we'll have this result. So let F be a field. P be a maximum partial order on F if J sub P is not 0. And this P must be directed. So we prove by contradiction. Suppose E sub P is not F, then we derive contradiction. On previous result, we know F is algebraic over E sub P. So we can pick up a element in E, alpha in F, not in E sub P, because it's algebraic. So then this alpha will satisfy a irreducible polynomial. Because also E sub P is a quotient field. It's a quotient field of B sub P. Then we can pick up a irreducible Monic polynomial for alpha over B sub P. Just like if we have polynomial irreducible over Q, then we can make this another irreducible polynomial over Z. Okay, so basically that will be the same. Now, Dubois define this P sub 1. So, this degree for this irreducible polynomial is n. So this will consist of all polynomial in alpha degree utmost is n minus 1. So the coefficient will be P. P will be an element in this maximal partial order. Z will be all elements in J sub P. So the key in the proof is addition. Show the addition is close, is easier. For multiplication, I think here is a trick because J sub P is ideal of B sub P. So if we multiply those A with J, then the result still in J sub P. Okay, so that's so it's a very nice construction. Now can show the P1 will be the preprime. So close under addition and the multiplication, not including 91. But P is containing P1, so they must be the same because P1 actually we also use this P is a preprime from the infinite prime. P is infinite prime. So P is in P1, and P1 is a preprime, so they must be equal. Now we pick up one element Z in case of P different from 0 because under that condition. Then this is polynomial. So we take P is equal to 1. That take a degree is equal to 1. Okay. That will be in P1. That will be in P. Then we minus 1 both sides. So Z times alpha will be in E sub P. Now we take the inverse of Z both sides. Because P is a total field of B sub P. So this Z is in J sub P, that will be in B sub P. So the inverse will be in E sub P because E sub P is the total field of B sub P. That means alpha will be in B sub P, so that will be the contradiction. We will assume alpha is not in B sub P. So that means the P must be directed. So basically, here's an idea in Dubois proof. So that F be a field with advanced degree over Q is bigger than equal to 1. Then F contains a directed partial order. So let's characterize the transcendental basis. Then we take a element X and consider polynomial ring Q. And still we order this polynomial ring by define a polynomial is positive if the coefficient of term of those term of power is positive. Then this will be a so denoted by P T, the positive cone of the total order Q of X. T will be a partial order of the whole field of F. So this T is containing a maximal partial order. Now 1 plus X for any integer will be in T because this low is a term, coefficient of low is a term is 1, always positive. That means this X will be in J sub P. So X J sub P is not 0. So if J sub P is not 0, then by theorem 12, P will be a directed partial order. After Dubois proved more, so he proved that there exists at least 2 to the D and the cardinality F are directed partial orders on the field. Finally, I want to give a characterization of a field which is not algebraic over here. So a field is not algebraic over field if and only if F has a directed maximum partial order with negative squares. One direction is clear. For this direction, suppose F is suppose F has a direct partial order with negative square. I want to show F is not algebraic. Yeah, I want to show another direction. One direction is clear. So if F has no direct partial order with negative square, that so I mean, if F is algebraic, then F has no direct maximum partial order with negative square, because we know the direct maximum partial order must be total order. So now we suppose F is not algebraic, take one element in F, non-algebraic over Q. Then we do the polynomial ring over V, and we define partial order on A. This way, so we evaluate the polynomial at I. If this result is not zero and also a positive integer, then we define this polynomial will be positive. Now this will be partial order on A, so we partial order on the whole field. Then P sub A is extended to a maximum partial order on F. Now consider Fx is equal to 1 plus x squared. Now for any integer n, 1 plus nx will be in P sub A, because if we evaluate the function at I, then we get 1, or we get 1, because this Fi will be 0. So by theorem 12, this will be directed maximum partial order. If we consider this g of x is equal to negative x squared, then we know this g of I is equal to 1. So then g of x will be positive. So that means x squared will be less than 0. So this will be a partial order of a negative square. And that's all we have. Here's a reference. Thank you. For infinite primes and order field. Otherwise, I won't consider infinite, because my work is on ordered ring and field. So when I read the paper, I saw this infinite prime and together with ordered field. And from here, then I know the Harrison paper finite infinite prime for ring and field.
Jingjing, I have a question. I'm sorry, where you go?
So, do you feel you understand now the difference between the maximal partial orders and infinite primes? I know, like every maximal partial.
Right, for
is-
if we consider integer domain, okay, more generally, not only field. If algebraic, then it will be the same. If not algebraic, then they will be different.
So partial orders give us ways.
Maximum partial order.
Yeah. Partial orders are general ways of making a partially ordered ring. But now you have these infinite primes. If you did something that you.
I was surprised actually, because nobody before mentioned this to me, but to me, Berkeley paper is from 1956, and Harrison paper is from 1936. But Harrison didn't mention any partial order in his book, and my advice store, we didn't mention anything, about infinite primes. To me, seems so. That's purpose of my talk. I want to just draw your attention. Maybe those who fields have connections. We can use the infinite prime to solve some questions in this ordered area. For example, for any ring, if it is strong Archimedean, then must be F ring. Because every positive element will be less than integer, positive integer. Stronger than F ring. F ring certainly may not be strong Archimedean, because we look at two copies of totally ordered like Z cross Z. It's F ring, but it may not be FZ, but some other any two copies of total ordered ring, but this may not be strong Archimedean. But yeah, so generally, if you have a ring which is a strong Archimedean, that must be F ring. But Archimedean certainly may not be F ring, right? For any ring. So Yeah, I just feel, if we consider field, but I don't feel it's useful if we consider field or integral domain for everything, because we know if we have everything for field, will be total order, and also for integral domain will be total order. That's for general ring, maybe you will consider arbitrary ring or commutative ring with a strong within, because all results proved by Harrison depending on strong within. If it is strong within, then there's a structure theorem. Otherwise, still don't know how to handle other situations.
Yes. Could you please go back 3 or 4 slides? You quoted a result of Dubois at there at the bottom.
Okay. Okay.
There. Yes, at the bottom, he proved there's at least 2 to the D times cardinal. Is F an infinite field or what? Up above, I thought it was infinite. So are you multiplying a finite number times an infinite cardinal, or what is that?
Yeah, the cardinality could be
Any, even a finite field, it would be correct.
But then that would be
that should be. Yeah, that's but anyway, I can double check later about this. I think he means if a finite field or a countable field, then this will be 0. I believe.
Okay, I'm not familiar with.
Should cardinality maybe be that something to do with the transcendence degree as opposed to cardinality?
No,
That's D.
right. So like a polynomial ring, transcendent degree will be 1. X is 1, but cardinality is still.
F has to be either countable or less than or equal to C.
I can double check.
The transcendence degree. Oh, yeah, good point.
Yeah, could be infinite, right, certainly, yeah. Yeah, could be infinite.
Oh, okay, so that's saying the cardinality of F.
Yeah, you have, if you have a,
Two to the.
yeah, if you
We're
have a.
multiplying infinite cardinal numbers.
Yeah, gotcha.
2 infinite cardinal numbers.
Right, yes. Yeah.
Yeah, possibly.
But hope, some of you, especially some young researchers, can make connections between those two items. Thank you.
Well, all right, thank you again.